related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. Here are a few questions that you should be able to answer based only on 18.06. A. Suppose that B is a Hermitian positive definite matrix. Show that there is a unique matrix square root B which is Hermitian positive definite and has the property square root B, 2 equals B. Hint, use the diagonalization of B. B. Suppose that A and B are Hermitian matrices and that B is positive definite. I. Show that B-1A is similar, in the 18.06 sense, to a Hermitian matrix. Hint, use your answer from above. 2. What does this tell you about the eigenvalues lambda of B-1A, i.e. the solutions of B-1x equals lambda x? 3. Are the eigenvectors x orthogonal? 4. In Julia, make a random 5 by 5 real symmetric matrix via A equals rand, 5, 5. A equals A plus A and a random 5 by 5 positive definite matrix via B equals rand, 5, 5. B equals B asterisk B. Then check that the eigenvalues of B-1A match your expectations from above via lambda x equals eigenvals, B\A. This will give an array lambda of the eigenvalues and a matrix X whose columns are the eigenvectors. MathHomeworkSolver.com. V. Using your Julia result, what happens if you compute C equals XTBX via C equals X asterisk B asterisk X? You should notice that the matrix C is very special in some way. Show that the elements Sig of C are a kind of dot product of the eigenvectors I and j, but with a factor of B in the middle of the dot product. C. The solutions y, t, of the ODE y minus 2 y minus psi equals 0 are of the form y, t, equals. For some constants C1 and C2 determined by the initial conditions. Suppose that A is a real symmetric 4 by 4 matrix with eigenvalues 3, 8, 15, 24 and corresponding eigenvectors x1, x2, x4, respectively. I, if xt, solves the system of ODE's AX with initial conditions x0 equals a 0 and x0 equals b0, write down the solution xt as a closed-form expression, no matrix inverses or exponentials, in terms of the eigenvectors x1, x2, x4 and a 0 and b0. Hint, expand xt, in the basis of the eigenvectors with unknown coefficients c1, t, c4, t, then plug into the ODE and solve for each coefficient using the fact that the eigenvectors are underscore 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 underscore. 2. After a long time t0, what do you expect the approximate form of the solution to be? MathHomeworkSolver.com. Problem 2. In class, we considered the 1D Poisson equation for the vector space of functions u, x, on x, 0, L, with the Dirichlet boundary conditions u, 0, equals u, L, equals 0, and solved it in terms of the eigenfunctions of, giving a Fourier sine series. Here, we will consider a couple of small variations on this. A. Suppose that we change the boundary conditions to the periodic boundary condition u, 0, equals u, L. I. What are the eigenfunctions of now? 2. Will Poisson's equation have unique solutions? Why or why not? 3. Under what conditions, if any, on f, x, would a solution exist? You can restrict yourself to f with a convergent Fourier series. B. If we instead consider conditions v, 0, equals dx2v, x, v, L, plus 1, do these functions form a vector space? Why or why not? For functions v, x, with the boundary. MathHomeworkSolver.com. C. Explain how we can transform the v, x, problem of the previous part back into the original problem with u, 0 equals u, L, by writing u, x equals v, x, plus q, x. And f, x equals g, x, plus r, x, for some functions q and r. Transforming a new problem into an old, solved one is always a useful thing to do. Problem 3. For this question, you may find it helpful to refer to the notes and reading from Lecture 3. Consider a finite difference approximation of the form A. Substituting the Taylor series for u, x plus delta x, etc., assuming u is a smooth function with a convergent Taylor series, blah blah, show that by an appropriate choice of the constants c and d you can make this approximation fourth-order accurate, that is, the errors are proportional to delta x, 4 for small delta x. MathHomeworkSolver.com. B. Check your answer to the previous part by numerically computing u, 1, for u, x equals sin x, as a function of delta x, exactly as in the handout from class. Refer to the notebook posted in Lecture 3 for the relevant Julia commands, and adapt them as needed. Verify from your log plot of the errors versus delta x that you obtained the expected fourth-order accuracy. MathHomeworkSolver.com. Problem 1. A. Since it is Hermitian, B can be diagonalized, B equals q lambda q, where q is the matrix whose columns are the eigenvectors, chosen orthonormal so that q minus 1 equals q, and lambda is the diagonal matrix of eigenvalues. Define square root lambda as the diagonal matrix of the positive square roots of the eigenvalues, which is possible because the eigenvalues are 0, since b is positive definite. Then define square root b equals q square root lambda q, and by inspection we obtain square root b, 2 equals b. By construction, square root b is positive definite and Hermitian. It is easy to see that this square root b is unique, even though the eigenvectors x are not unique, because any acceptable transformation of q must commute with lambda and hence with square root lambda. Consider for simplicity the case of distinct eigenvalues. In this case, we can only scale the eigenvectors by non-zero constants, corresponding to multiplying q on the right by a diagonal, non-singular, matrix D. This gives the same b for any d, since qd lambda, qd, minus 1 equals q lambda dd minus 1 q minus 1 equals q lambda q minus 1, diagonal matrices commute, and for the same reason it gives the same square root b. For repeated eigenvalues lambda, d can have off-diagonal elements that mix eigenvectors of the same eigenvalue, but d still commutes with lambda because these off-diagonal elements only appear in blocks where lambda is a multiple lambda I of the identity, which commutes with anything. MathHomeworkSolver.com. B. Solutions. I. From 18.06, B-1a is similar to C equals MB-1am-1 for any invertible m. Let m equals B1/2 from above. Then C equals B-1/2ab-1/2, which is clearly Hermitian since A and B-1/2 are Hermitian. Why is B-1/2 Hermitian? Because B1/2 is Hermitian from above, and the inverse of a Hermitian matrix is Hermitian. 2. From 18.06, similarity means that B-1a has the same eigenvalues as C, and since C is Hermitian these eigenvalues are real. 3. No, they are not, in general, orthogonal. The eigenvectors q of C are, or can be chosen to be orthonormal, q chosen to be orthonormal, q equals I, but the eigenvectors of bq equals I, but the eigenvectors of B-1a are x equals m a r x equals m-1q equals B-1/2q, and hence x equals q B-1q equals I unless b equals I. 4. Note that there was a typo in the set. The eigenvals function returns only the eigenvalues. You should use the eig function instead to get both eigenvalues and eigenvectors, as explained in the Julia handout. MathHomeworkSolver.com. The array lambda that you obtain in Julia should